Have you ever just stopped and wondered how these incredible AI models we hear about every day are actually built? Well, it's not magic, and they're definitely not building them from scratch. Nope. It's all done using these powerful toolkits called deep learning frameworks. So today, we're going to pull back the curtain on these essential toolkits, the very foundation of modern AI. Okay, so here's our game plan. We'll kick things off with the big picture, why these frameworks even exist. Then, we'll dive right into their core components, things called tensors and graphs. After that, we'll put the two giants, PyTorch and TensorFlow, head-to-head. And we'll wrap up with one of the absolute golden rules for training any model.
All right, first up, why do we even need these things in the first place? And who are the major players that have basically shaped this entire AI landscape? So, to get at that big question, you have to realize that developers almost never start from zero. You can think of frameworks as these really sophisticated construction kits. They give you all the pre-built, super-optimized parts to handle the mind-bendingly complex math, so developers can focus on the fun part, the model's actual design and logic.
And, this field has evolved at absolute lightning speed. It really started to get going with a framework called Theano, but the whole game changed in 2015 with Google's TensorFlow. Then, in 2017, Facebook's PyTorch showed up, and it championed this more flexible, dynamic approach that researchers just fell in love with, mostly because it was so much easier to debug. This kicked off a massive rivalry that honestly pushed both frameworks to get way better, with TensorFlow eventually adopting PyTorch's flexibility and PyTorch adding powerful compilers to catch up to TensorFlow's speed.
Okay, so how do these frameworks actually build anything? Well, just like any good construction kit, they start with the most basic building blocks. And in the world of deep learning, that fundamental block is called a tensor. So what on earth is a tensor? Well, at its heart, it's just a container for data. Think of it like a superpowered container for numbers. It could be a single number, a list of numbers, a grid of numbers like a picture, or even a cube of numbers that represents a video. This idea is so central that Google's framework TensorFlow is literally named for how data, tensors, flow through a model.
So you might be wondering, why not just use a standard Python list? Well, this slide lays it out perfectly. Tensors are like rockets. They are specifically optimized for the insane high-speed math you need to run on GPUs. A regular list, on the other hand, it's kind of like a turtle. It'll get the job done, eventually, but it's just way too slow and clunky for the massive multidimensional data we use in AI, like all the pixels in an image.
All right, so we've got our building blocks, the tensors. Now what? How do we tell them what to do? That's where the blueprint comes in, the computational graph.
A computational graph is basically the recipe for your neural network. Every node in the graph is a math operation, like adding or multiplying something. And the edges, those lines connecting the nodes, show how the data, our tensors, flow from one operation to the next. This graph literally defines the entire journey of your data, from the moment it enters to the final prediction. And this brings us right back to that philosophical split we saw on the timeline. The original TensorFlow used static graphs. You had to define the entire blueprint up front. Now, this was great for speed, but an absolute nightmare to debug. PyTorch came in and championed dynamic graphs, which build the blueprint as the code is running. This was a total game changer for flexibility and made it so much easier to find and fix your errors. Okay, with those core concepts under our belt, let's zoom out and see how the two industry giants, PyTorch and TensorFlow, actually put these ideas to use in the real world. So they both get you to the same place, just with totally different philosophies. TensorFlow, especially with its Keras API, is way more streamlined. It gives you these simple, powerful commands like .fit, so you can get up and running really fast. PyTorch, on the other hand, is more hands-on. It basically gives you the keys to the engine, making you write out the training loop step by step, which gives you incredible fine-grained control. And finally, having these powerful tools is one thing, but using them the right way is a whole different ballgame. Let's talk about one of the most critical best practices, how to train a model that actually performs well on new data it's never seen before. This is all about avoiding a nasty problem called overfitting. Okay, here's a classic trap. You know you're not supposed to train your model on your final test data, right? But what a lot of people do is they tweak their model's settings, the hyperparameters, based on how well it's doing on that test set. If you do that, you're basically letting your model peek at the final exam answers while it studies. Sure, it might get a great score on that specific test, but it hasn't truly learned the material. The solution is a three-way data split. First, you've got your training set. This is the biggest chunk, and it's used to teach the model's main weights. Then you have a validation set. This is the data you use to tune your settings and pick the best version of your model. And finally, you have the test set, which you only touch once at the very, very end to get a final unbiased score. See? Each slice has a very specific job. But what if you just don't have enough data for a big validation set? For that, there's a really powerful technique called K-fold cross-validation. Instead of just one validation set, you split your data into multiple folds. Then you train your model several times, rotating which fold is used for validation each time. By averaging out all the results, you get a much more robust and reliable idea of how your model will actually perform in the wild. Now, the trade-off, as you can see here, is all about performance versus cost. On the plus side, you get a much more stable and trustworthy estimate of your model's performance. But on the other side, it is computationally expensive. I mean, with 5-fold cross-validation, you're training your model 5 times just to get one result. It's powerful for sure, but that power isn't free. And this brings us to a final, bigger question. The tools we have today, PyTorch, TensorFlow, JAX, they're incredibly powerful. The barriers to just building AI are lower than they have ever been. So what's the next great barrier? Is it about finding better data, inventing more clever algorithms, or is it something else entirely? The tools are ready for us, but they're just one piece of a much, much larger puzzle.